I'm audible. Yeah. So, good evening, all. So, let's start on session five. So, let's start with this question. So, in the first question, it is asked that a crystalline phase of PiCl3 was generated in situ from TiCl4 and Al-artemisinin alkyl groups and in hydrocarbon solvent. So, in the original work, olefin polymerization reported by Ziegler. Just they wanted to know what kind of TiCl3 Professor Ziegler used for his catalysis to make that polyethylene type polymer. So, this is a part of Ziegler-Natta uh, reaction condition. So, actually, in the paper, we follow. Uh, Beta TICL thing. So there are some aspects of this different kind of TICL thing. So let's just discuss about this. So you have now discussed for some times or couple of times about Ziegler-Natta catalyst and how they work. So today I am going to show obviously basic properties of particular catalyst and how that alpha, beta, gamma, delta, this kind of variation of TiCl3, this particular catalyst would dictate the microstructure of your polymer. And let's discuss that. So, this is a obviously Nobel winning catalyst by these two professors, Ziegler and Natta. So they got original this Nobel Prize in 1963 for the contribution, and these two catalysts are combination are mainly they have used ICL4 LET3 and TiCl3 LET3. This one by Nata, this one by Ziegler. So monomer are like uh, non-polar alkenes with this kind of for poly ethylenes, polypropylenes, this kind of things. So these are actually co-catalyst aluminum-based reagent. They activate that the titanium site, and that's how that thing progresses. So uh, uh, this consists of transition metal active site of uh, uh, as spoken. So what we are telling that aluminium, which is present in the reaction condition like this, it coordinating with fluoro compound with titanium and act as your co-catalyst. And most of the transition metal is titanium based, like tetrachloride, trichloride, this kind of, and bromo or iodide, they are also used. So this is the basic reaction condition, and with signal nata you can get this kind of polymer. So that's the primary thing. So, but so here one of the great observation for signal nata catalyst was when they did reaction with poly this particular propene molecule, they got this kind of stereochemistry. All are isotactic. The tacticity we have learned already. These are isotactic units, and uh, if let's say if you have this kind of system, then they are indiotactic, but they are all are in the same plane above there. So they when they charged this particular reaction condition, they only observe this particular formula. So now the question is how this thing is happening. So Um, so here, so we will discuss that. So now coming to that first question, what they have asked, that what kind of TiCl3 they have used. So this is listen. So beta TiCl3 they have used, and normal hydrocarbon solvent, and uh, uh, and for this kind of polymerization. And what the difference between alpha, beta, gamma, delta. So they actually dictate the stereochemistry. So for beta TiCl3, they are the color you can differentiate them. So beta TiCl3 are brown in color, and for alpha, delta, or gamma, they are violet in color, crystalline. So that's one of the identifying factors for these two. And so, these are the types of titanium-based catalysts people have. Now, coming to the set of reactions. So, when TiCl4 reacted with this particular aluminum-based reagent, at first what happens is one of the alkyl group is exchanged. So, this goes through this kind of transition state, you can say. And so, here you can see one of the fluoro is incorporated in aluminum, and one of the alkyl groups is equal to titanium. So, that's how one nickel center is created. And that's how that mechanism progresses. So that's one of the uh, initial reaction that happens to activate your titanium compound so that it can do that particular polymerization reaction. Now, this PiCl4, reacted with aluminum and with this kind of reagent. Now, you can say that so this particular thing is now reacting with your titanium fluoride compound. And in the same way, fluoro can be exchanged and you can get this kind of thing. So in that way, the variants actually can react with your compound and you can have that this kind of activation. For the this aluminum, that's why that aluminum reagent is very much important. And from here, actually, you can say your chain propagates. So R dot is generated and you can start your polymerase. So that's how things starts initially. So for the reaction, so there are many reaction are proposed, sorry, mechanism are proposed, how that signal catalyst behaves and how it do its polymerization, how stereoselectivity comes. So there are many proposals. So there are some of them. So, firstly, Carrick, Carradini, so Sebor, all and many other scientists have proposed this particular mechanism, and so we will discuss about that most accepted one. Okay. So, when one of the R group is so you are seeing that this is PI actually this particular compound CL3R, and they are actually connected with different cytokines. So it is not in like monomeric form. So it is also in polymeric system type thing, and um, uh, it actually presents in some network type somehow. Coordination happens like that. So there, after this particular chloride removal and R group incorporation, what happens is one heptane side is created, and this is very much important to start your cycle. So here you are seeing that three-dimensional structure of alpha TiCl3. So there you can see this kind of vacuum side are created in that way, and uh, uh, and uh, they actually responsible for your polymerization reaction. And these two are enantiomeric phases, so you can see easily. So in the network, if these two things are present, then these two are responsible for two enantiomeric points to be formed, and that would be syntactic polymer. That regarding this kind of system. So this is the mechanism how Procel uh, Earlman mechanism 1964 they have. So at first this vacuum slide is created. Then this is reacted with your olefin unit, mainly that propene we are discussing about. Now after this vacuum side and this olefin, they actually react fast, and they form this kind of system. So here you are already seeing that so it is already dimeric. So what happens in initially? So when training in the from some middle step, but you can just see that say that this is C3. And in the same way, the first chain formation or bond formation dimer would form, then the chain would propagate. Uh, Mechanism is same. So after this thing, so here you are seeing that this kind of uh, full member transition state is forming means this kind of uh, one formation is there, so that you have this particular full member transition state. Now migrated insertion would happen means here what happens is this particular bond is formed and this bond is split. So that's how your migratory insertion happens, and you have this kind of system. So the chain is elongated like with one unit. And again, you are seeing that a particular vacuum side is created. So for that, the next monomer unit can appear, and this thing can elongate. So here, one of the important thing is these two happen. Uh, that a backflip means this particular backend side is extends like this, and you can have this kind of system. And it is actually important here so that you can maintain your this particular this kind of system. So for isoselective or isotactic polymerization, this particular backflip is very much important. So that whole polymer does not migrate, only the tip side end migrate. So that's how this thing happens. And uh, this particular required for isoselective polymerization and regeneration of the original configuration in the backend side and for yeah, um, these things are required. So, polymerization obviously occurring in the active side of the let's say means surface. So, it is a heterogeneous reaction, not homogeneous. So, in the surface, only the reaction is happening. And that polymerization at the active site influenced by electronic and spherical environment. Obviously, so here this flip, you can say this thing can also be controlled with sometimes the spheric and this ISO or thin dio that also depends of with this full membering. When you have this full membering, then you have this kind of interaction. So sometimes they are also responsible for this flip to happen. So stereo or steric environment, these things and the electronics both are very much important for um, dictating this stereo centers. An active sentence can occupy very obviously general statement and polymers with the word are often. So it's one of the reason why your Zignanata catalyst is very much popular because you can get high molecular weight polymerization, which is not possible with normal uh, radical based anionic or cationic polymerization. So that's why this is pretty much efficient when you need high. Now, for stereo selectivity, so these are the you can say this is the some facts that need to be known. So alpha, gamma, delta, this particular versions of TiCl3 is much more efficient for your stereochemistry. Then TiCl2 and TiCl4 and beta TiCl, they are works in the this particular titanium elements. So there's the uh, important statement that you need to know for stereo selectively doing a reaction. And for a different hello atom, so here you are seeing that fluoro ones are the base, then a bromo, then iodo. And for fourth system, all are equally efficient. So, what are the difference between these four forms? So, for gamma TiCl3, that Cl minus is in cubic close place. So there are differences that crystal networking actually, and the dynamic that microstructure is responsible for a different versions of this TiCl. For alpha one, it is in hexagonal close packing, and for delta, these are the mixture of hexagonal and cubic, right? And for beta, they're actually linear or chain type packing. So that's why the stereo selectivity is less. So for this particular beta version, so half of the Ki atoms have two vacancies. So that's why this stereo selectivity is low, and for other this particular systems, you have one vacancy. That's why stereotypically is higher because when you have two vacant sites, so any of the phase active site your uh, molecule can access means when the flip happens or when the monomer is approached to your titanium based thing, so any of the phase can react, and that's why you lose the control. But stereotypically, because both of them having different stereo properties, so that's how the stereotypically is little bit hampered when you use this beta and CL3. So that's the reason beta CL3 is not as much efficient as this three are. Now coming to vanadium. So when you use vanadium, you would see you would end up with symbiotic polymer. But with titanium, what we are seeing that with titanium we can maintain your isotactic. Hmm? All are same. But for vanadium, when you use that, so you would have different. But looking at the reaction, so it can be said that kind of same thing is happening. But how these differences come? So that can be explained with particular mechanism. So for vanadium, what happens is the initial activation is the same process. Like one vacuum site is created, then it reacts with your olefinic unit, and you can have this particular interaction, then migratory insertion, like that this way. But now for titanium, what is happening there was that's the for this case, you are seeing that this thing is not happening. So that's due to the nature of vanadium or pure, uh, electronic and stereo effect both are there. So that's the reason this backflipping, what is happening for titanium that is not present, but that's why it needs to incorporate from the other side and use this R and S in that way. Information is pumped, and then you get this syndactic chain. That's how. But vanadium, with vanadium, you can control your selectivity of your the nature of your molecule. Now, so that's how the cell was actually with the TI chain. Now coming to your second question. So this particular reaction we have given with zirconium and with MAO and at first initiation I start giving initiating species. Then it reacts with your monomer. Monomer get activated uh, initial propagating series and then lastly mm, this thing progresses in that way propagation. So that during polymerization of metallocene and MAO catalyst, the step two reversible and slow. So they want to know the correct order of polymerization with respect to mono. So for that, just need to discuss about these three steps and do the kinetics. So zirconium-based reaction they have written there. So mainly if you say in the real example, so they are that uh, these metallocenes actually where this kind of system are used and as MAO, so boron based reagent, this particular Lewis as seed is used. And with zirconium and this boron, they actually at first interact with each other and have this anionic boron, this kind of this kind of intermediate or initial uh, activating species is present, in that particular this kind of way. So what is happening that one of the C3 is just transferred to your boron as it is a Lewis acid. So you have now zirconium plus. So here it is cationic and this anionic. So in that way, two counterparts are there: cationic metal and anionic but Lewis acid. That's how this thing happens. So this is the initiation step. Obviously, stoichiometric amount of these two are needed. Now, this is for one of the case, and second, what is happening over here is we this kind of thing also can be used where this is already in this state. But again, these are counter anion and cationic. So the same way actually. So this cation to C3 is transferred like this, and you activate as its cationic form. So that two strategies how can you can activate your zirconium based addition. So Lewis acid or this kind of borate starts or that. Now coming to your mechanism. So now like borane what you are using. After that, you are generating this kind of system where you cationic species is there. So when the cationic species is there means you have one deficiency and it can actually react with your so it's nothing but your I star. And this is reacting with your monomer. And after uh, this particular propagation and this thing you are generating your propagating monomer that's how this thing progresses. So monomer at the other side of vacancy and polymer that's how it happens. So with that fluoro would be taken up by that lead. Now let's discuss about that. Well, your kinase. So with co-catalyst with zirconium with first step is obviously reversible and I star the cationic species what you are forming. This is I star. Deep initiations. This is first. The next step is happening. So let's consider it as K1 and equilibrium consider as K1. Now for this particular step, again reversible. So you can consider is that initial propagation step as K2. And this thing, propagation with MM cell is this K2 step. So when you write this one, uh, obviously uh, you can write it as this kind of way. For this step, so the second step, if it is reversible and fast, you can say means it is like this. You can say this I star and M star they are equal in concentration because it's fast, and the rate would be like this kind of fashion. So for this case, you can see that with respect to monomer, it is faster. So with normal how you define that rate, you can do that. You can end up with this particular equation. Now, when if we reversible and slow, these two not are in equilibrium fashion and they are you can say this kind of their concentration is different. Then the rate which you are going to end up with, then here you are seeing that particular. So that's how it's now order is the second order of your book. So that's the thing actually for this. So if step two is reversible and fast, you have this equation where it's actually in that way where you have this thing and it is first order and for this reversible and slow it is second order. Let's take what they have asked us up here. They ask about I think reversible and so that would be second order. So appropriate co-initiator and initiator, Mao versus that zirconium catalyst. So their ratio is so they are information code based code. So C, they are generally 1000:1 kind of ratio, and with that you can do that. Now doing polymerization with propylene and aluminum heat following FCC that is occur. So this thing we have already explained. So how vanadium reacts uh, uh, with your monomer unit, and for that here you can see they are kindred classical this. So they are chain control. So at first, in the same way, that tip site would be forming after its reaction with aluminum-based reagent or Lewis acid. Then this monomer would be coming here like this way. Then that this particular uh, thief, and again you are this this thing that forming but thing would be forming, and you have this particular compound. Now for titanium, what is happening here is backflip. But here this particular backflip is not happening. So that's why the second monomer that would be coming would be but here, and you are going to observe that R and S is kind of conformation because it is now in different phase. If the flip is happening, then only you would end up with same phase methyl or monomer unit incorporation. But as the backflip is not happening for vanadium, so you are end up with this and attractive physiotherapy. So it would be For this question, we want to us to predict the major product for this particular reaction condition with zirconium-based allicin and monomer with MAO activation. They want to know what kind of thing that going to be formed. So let's discuss about this little bit. So this is the metallicin and two catalyst um, aluminum based one. With activation, you have that one active site with cationic active site. So that's how that your reaction progresses. Now, if this at first pi would be donated like that, then four member with egoistic interaction followed by this insertion. In the same way, it would propagate. But now, the question is the chirality that would be happening in polymer. So when you would use this kind of system, so this particular catalyst actually they have given over here. It is actually not uh, chiral actually. Exchange or movement of ligands are faster than olefin insertion. So their movement or exchange that is quite faster. So than your olefin insertion. So that's why they are not that much stereoselective way you can expect. So no order is there. So R is that thing can happen in any way, and that is not controllable. So that's why a tactic polymer would be forming. Means there are some disorders should be there, and the disorder that are not controllable. Somewhere you would say this kind of mesotactic diet, sometimes it is racemic diet, sometimes meso diet. So this thing we you would observe, and they are not controllable. So with this kind of system. So to stop this particular expense, what people do actually, or scientists do is they actually this kind of ANSA system they are doing. So they just fix these two allicin units with one atom with the carbon chain or any other atom so that they cannot flip around and in that way that they want to control that. So then only you can have chiral catalyst and you can do isotopic loss in the electric polymerization. So for this particular system and some metallocene, the arrangement you can see there are three possibilities actually. So here for this system, they are not no plane can be passed because it is pointing towards you and it is pointing outward. Sigma plane passing over here is not possible. So these two allicins are in different direction and if you do the nomenclature arrays, one would be R and then another would be S. So one mirror plane you can express and they are not super impossible. So that's why they are receiving mixture. And another form is this kind of form. So here both of them are uh, pointing towards you and outwards, and here you can actually pass that sigma plane. So this is a meso compound. And for this, uh, if you use this particular thing, it would you can uh, the result would be okay because it is not chiral molecule, so there is no control with your catalyst because it is chiral molecule catalyst and with chiral control polymerization, sorry, the catalyst control polymerization, the chirality of the catalyst is very much important to maintain that specificity. But here it is the chiral molecule, so you end up with atactic polymer because the chain would be chain end would dictate that stoichiometry and that cannot be controlled easily. But for these cases, R or S, so if you have used this ethnic mixture, both of them you would end up with your syntactic polymer. Because one would give your R product, another would S, so that would be syntactic polymer. And when you use, if you can use only R enantiomer and only S enantiomer, then you can expect to form isotactic polymer. Means if you, let's say, use R, you end up with this kind of system. And if you use S, you can end up with this kind of system. That can be controlled if you use pure one of the enantiomer. You can, and if you use enantiomer, means the mixture of them 50-50, then you have to end up with that. In that way, you can this can dictate things. For this kind of setup, so this is a chiral setup and no plane of symmetry, only chiral axis is there. And so isotactic, both the binding sites have same chirality. So if C2 axis and the chiral molecular axis, and obviously isotactic polymer you are going to form. So here you can see that this is not a chiral plane. This is not a sigma plane. This is a chiral plane because these two are different and they are not impossible. So they are not sigma plane. This is a chiral plane. So here you have a plane of symmetry, and for this you have a plane axis of symmetry. So it is also an chiral molecule, and you can end up with syntactic polymerization of your unit. Each binding side is locally chiral, two binding have opposite chirality. So the two binding side of this having different chirality, so that way or in that way syntactic polymerization. And that what we are telling earlier, that chain in control, if you follow uh, uh, so that chain would dictate your thing. So if you have a error, now this should carry forward like this. So error cannot be uh, 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 removed, and this error persists. And for at least site control, that error can be repaired. And here you are seeing this is error, but after that the error is repaired. For this case, that thing is error is continued. That's the difference between chain end and uh, catalyst side control. So, continuing that thing. So, for this case, here you are seeing that tactic diodes are like this. After that, you have generated one receiving that, and this is the errors. And after that, it is modified, or it is corrected, repaired. But for this case, it is in control. So once your error is there, that error persists. The error is going to persist in that way. So what kind of error is that? So that can be dictated obviously with this thing. So if you have chain in control, uh, this one, so then you have only one this may show and receiving that, and accordingly NMRP you would create, because for receiving that you have that different signal. uh, for receiving you have same signal, and for meso you have different signal of these two proton, right? So when it is meso, these two are chemically different, and when it is uh, when it is racemic, these two hydrogen have been chemically equivalent. Chemically equivalent there. So in the Murphy you can. observe that, and you can say what kind of mechanism you are following. Is it chain in control, or is it catalyst in control? But here you are going to have only one, sorry, not one. You are going to have two this diet MR and MR, two diet mesolecinic would be forming two these diets. But, for this case, only one. That's how you can dictate this thing. And this case also you are seeing the same thing. So for this case, we are doing thin diet tactic, and in thin diet tactic, and that error we can say. And for this case, let's say you have for this case it is thin diet tactic. So for this you can also control that. For this case also you can observe same kind of thing for thin diet tactic. So here you are seeing that glycemic diets are maintaining like this. Now you have one error over here. It become meso. So after that, it needs to be get repaired, and it been repaired. That's how this thing again continues like this. So only error is this point, and these things are repaired. So, because to if it has, let's say, non-error, then you have this kind of system. So no error is there. Here only one error. So this thing should be below, but it is above. So now next thing from next point point, it is being corrected as you are using catalytic statement. It is corrected. So for this again, you are seeing only two MR two these two diodes, and rest of the things are like for chain in control. Once one error is there, with error persists. So persists. So this error now continues. The brain, you have this only one this kind of thing, and if you calculate again, you are going to observe only one. So with the NMR display, you can decide which kind of error is this, or which of kind of mechanism that you are dealing with. So, some features of metallurgy actually. So when you are using titanium, so they are less active and less stereospecific. And when you are using zirconium base, they are better activity and better stereospecific. With these again, they are less active but uh, less reactive, but stereoselectivity increases isometric. And shorter bridge increases activity and nucleophile decreases selectivity. Now coming to our uh, question, what is asked, and it is as a meso compound because mesochiral, but this exchange can happen, so it is not chiral. So here you end up with chain and control mechanism CEC. The things are like CEC or CSC. So this is CEC. So you are obviously going to end up with that. Fine. Now coming to next question. So now following questions are based on this itself. This itself. So again, here it is. That sigma plane is different. Right? It is a meso compound. So it is not chiral. Mean okay. In thing would be there. So chain in control and CC would end up with that. But this what they have asked that the following error when so this is the error and in the microstructure is generated while polymerization of propylene as shown below figure which represents a fragment and this so gives the most possible mechanism. So how we have learned earlier. So if you have one MR is then in control if you have two MR means this mesoracemic, so then that is your catalyst site control. Yes. So for this now let's look at here you have these two MRs to the catalyst site. Easily you can solve them and with NMR also it is pretty much detectable and you can do that. If there is no error, there here it would be above. So here you are seeing that actually. So here error is there, but from the next step itself, the error not persisted. As we are using catalyst and that only solely dependent upon your catalyst. And somehow one error came in the next uh, thing that catalyst to rectify itself and you would again see mm, corrected version. So it is a catalyst type. Now for this, the correct statement they are asking. So here you are seeing that there is no plane of symmetry because here this point it is pointing here and it is pointing over here. Sigma plane is not present, so there is no plane of symmetry. Obviously, C2 axis is there in that in this way, I think. So let's go back. So in that this way, C2 thing would be present. Uh, C2 is present. Consists C2 approximately chiral molecule, obviously. No sigma plane, so obviously it's a chiral and it is so this one is so this will so go your indirect, right? We have just learned this. So not symbiotic, sorry, isotactic. Isotactic for this case because both binding sites have same content. into this isotope. Now, the statement about mouse survey I have been suggested which character acts as a co-catalyst, obviously. So we have learned this here. Uh, Rate constant here. So there you are seeing that there. So one of the fluoro needed to be go there, so that's why it is used, and it is a co-catalyst because it is activating your zirconium. So there, so this is a Lewis acid formation of this cationic system is important to activate your catalyst and followed by your incorporation. So that's why it is needed. So the result is in the tactic while polymerization. Uh, tactic must go because what we are doing here is so Mao cannot separate that, so that fully dependent upon your zirconium based metal what you are using. Is it chiral or achiral meso? That all things are possible. So that depends upon this, not with mouse. So with using only mouse, it cannot specify that you would end up with symbiotic polymer. So it can give you symbiotic, atactic or isotactic. Any of them can be possible. So the only thing is that is fully dependent upon your metal steel, not catalyst. And it is highly soluble in any solvents, so not soluble because uh, 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 they are actually polar compounds, aluminum based, so not soluble. Maybe would be the right answer. So this reaction condition, what they want to do is with butyl lithium. Let's say if you have this compound, you can have this, this, this acidic proton because after deprotonation, you're going to end up with anion, and that system that you are generating would be uh, your that they are aromatic system because they are nothing but CP unit like this with uh, with the benzene. Right? So that's why that acidic proton and after deprotonation uh, like this, like this, you are in the place to anionize this this kind of fashion. override elimination would end up with your this kind of system. Uh, Totally with that. This is the ultimate compound that you are going to input. Now the question is the STOI. So that we have learned already. Now go back to this kind of system. So this is actually good thing. In this table, we can explain that. So this kind of system we are generating. So we have one extra this and rest of the things are same. And for this case, so the same way you can expect the same thing to happen. Like this. So if it is in this fashion, so hemoglobin will not be fast. So this would be their RNA one stereoisomer, this another stereoisomer, maybe followed the last three stereoisomer would be considered. So that's in that way you can explain. So this kind of case actually, we here you have see. So in that way you can explain this particular foot pain and you are going to end up with the uh, equation R is at and measure. These are the three options that you are going to get. হ্যালো? হ্যালো? হ্যাঁ, বলছি। ছিল। হ্যাঁ, হ্যাঁ, হ্যাঁ। হ্যাঁ, আপনাদের রুম নাম্বারটা কত? আমার হচ্ছে M311A। এই ৩১১ এই। কোন সাইডটা? এটা হচ্ছে ওই TRC। কাঠজোড়? হ্যাঁ, হ্যাঁ, ফ্লোরে আচ্ছা, আচ্ছা। মানে অমিতাভ স্যারের ল্যাবে তো দেবে? হ্যাঁ, ওই ক্যাফেটেরিয়া আছে না? হ্যাঁ, হ্যাঁ। ওখান থেকে ইয়ের দিকে যেতে কেমিস্ট্রি অফিস যেটা আছে ওই দিকে। 311 এ। আপনি কি এসেছেন? হ্যাঁ, হ্যাঁ। ল্যাবে এখন কেউ নেই অ্যাকচুয়ালি, ইয়ে হচ্ছে তো কনফারেন্স আছে। আমি কেউ অ্যাভেলেবেল থাকতে পারবে না একজন। আমি আসতে পারবো। আহ কতক্ষণ আছেন আপনি? আছি মোটামুটি। আমি তাহলে ধরুন 15 মিনিট পরে আসুন। আমি আসছি তাহলে। হুম, ঠিক আছে। In that way, we can describe how much QSMR can be formed. Now, into this question, so they are very easy. Electricity. So electricity is not observed. So for PVC, we all know electricity would be there. Here, the studio center would be generated. So it's a prochiral center. So there you have polystyrene again. For styrene, you have this prochiral center. Polypropylene prochiral center is there. But polyethylene, these are not prochiral. So here you are going to end up with this, and all are page two means no chiral center is there. So without chiral center, you cannot generate toxicity. So the option would be D. Uh, we just learned about these things, metalloallicin. So this is organometallic. They are inorganic polymer. This Nobel Prize, they want to know that at Nobel Prize 2000 discovery of alkene. So I think this we will discuss in the next meeting. And today, if you have any question, you can ask, or you can in this session. So, okay, again, thank you for joining today. If you have any question, you can just tell or and mail me also. So for today, we can end up here, and next day we will continue our discussion. So again, thank you for joining.